Hello everyone, we're going to do another dynamic programming question today. This one is called Oceans Anti-11 with a difficulty rating around 3, so definitely not a beginner question, but the question itself is very easy to understand, as in it is very easy to explain what it's asking. In this question, we are asked to generate bit strings of size n, that is, string consisting of only zeros and ones, which doesn't have any consecutive ones in it. Well, actually, you don't need to generate the bit strings. You just have to work out how many bit strings of length n do not have any consecutive ones in it. For example, here you can see two different bit strings. The first one is a valid bit string because there are no consecutive ones in it. Every time you see one, it'll be followed by a 0. And the second string you see here is invalid because there are 3 ones bunched together here. So that is an example of an invalid bit string, which you should not count. Here are more examples. If n is equal to 2, there are 3 valid bit strings. Obviously, just the one is invalid. If n is equal to 3, there are 5, and if n is equal to 4, everything in this column is valid, and everything in this column is invalid. So hopefully it's clear what you have to do. And if we look at the sample inputs, you're going to get the number of cases as the first input. And then for each case, they'll just give you a number, and you have to output the number of valid bit strings for that value of n. You just get the value of n as the input. So with n equal to 2, as you saw earlier, the answer should be 3. So hopefully it's clear. And we'll start by going to the drawing board and try to do this using recursive backtracking. Why start with recursive backtracking? Well, because it is a brute force method where we try every combination, so we should be able to get the answer for most problems. Of course, the question is, can we get the answer fast enough? And for this problem, I can tell you right away, no, because this is a dynamic programming question. But it's a good starting point because, as I mentioned in the other video, dynamic programming is basically brute force, but done better because you store intermediate results. So let's think about how we break down the problem into the subproblems. And this is how I visualize the problem. If you have done the recursive backtracking questions in the previous videos, I'm sure this will make sense to you. We start with an empty string. On every level, we either pick a 0 or a 1 and append it to the string. So you get a different subproblem depending on your choice. You go left if you pick a 0, you go right if you pick a 1. And if we do this 3 times, for example, we'll get bit strings of length 3. So these are all the possible bit strings you can have at the bottom. And every one of these nodes contain a unique string. So the number of nodes at the lowest level is the number of combinations that we can have. In fact, if this question only asks you how many different strings of zeros and ones of length n are there, then you don't need to do any recursive backtracking because the answer is just going to be 2 to the power of n. In this problem, though, we have to make sure that we don't pick 1 twice. So from this tree, you can see that from this node, if I pick 0 and then 1, then I'm not allowed to pick 1 again. And also, I can't have anything starting with 1, 1. Well, actually, I can't go to this node anyway because I'm not allowed to pick 1 after picking this one. So all the gray out nodes are not valid. So how do we make sure that we only generate the valid bit strings? How do we make sure that we don't pick consecutive ones? We can control this in our recursion. In fact, it's always good practice to try and code this, so I'm going to start with that. But before you watch the next part, perhaps you can give it a go as well. Try to write the recursive backtracking answer yourself first. If you don't know how to do this, then you should check out the other videos on recursive backtracking. If you think this is easy, well, I think you should do it first anyway. Prove it to yourself that you can do it. Write it out in a few minutes because it's always good to do small exercises such as this. Remember also that we don't need to build the actual string because we only need to work out the number of valid bit strings in the end. So this is going to matter later when you see it in the code. But if you write in the code yourself, just keep that in mind. You don't actually have to store the strings. You just have to work out if a string is valid or not. So the idea is you will have to go to the bottom and then you just return 1 for each valid combination. Okay, I have written some code that will handle the input and also the output for later on. So we can start by writing the recursive function right away. I'm going to call it generate, I guess, because we're kind of generating a bit string. So I'm going to start with an empty string at the top, and every time I call the function, I either add a 0 or a 1 to the string. But as I said, we don't actually need to store the string anywhere because we don't care about it. We just care if we get to the bottom of the tree. So I don't need to pass a string around. I need to return an int because when we get to the bottom, that's what we're going to return. That's what we're going to return. We're going to return a 1 if we ever get to the bottom here for each valid bit string. And for the input, well, we need to know how many bits we have appended so far, like how long the string we have so far. And that means we need a variable n. So you can start the chain with n equals 0 and going up to whatever length you want, but that means you have to pass two variables. It's easier to just start with n equaling to the length that you want and then keep on reducing n every time you call the function. So if you want a bit string of length 3, you start with n equal to 3, and next time you call it, n equal to 2, n equal to 1, and then when it gets to 0, you know you're at the bottom of the tree. So we're going to have n as the input parameter, and let's just write the stopping condition. So if n is equal to 0, I'm going to return 1. And what else do we need? Well, if we want to append a 0, we're going to call this function again. We're going to recursively call generate. So, and we have to keep track of the number of bit strings that it can generate. So I'm going to put that inside a variable count. n-1. That will take care of us appending a 0. And if I want to append a 1, then I'm going to do this. Of course, we won't be doing both. By the way, I hope this is clear. Line 21 means we pick a 0, so we have to generate another n-1 bits, which is the exact same call as you see in line 22, because here we pick a 1, but we still have to generate another n-1 bits, so this is going to be the same recursive call. It's just that we may not be allowed to do this line because the last bit in the string is a 1, so you can't pick another 1. Which means I also have to pass that information. I have to be able to work out what is the last bit we pick in the string. So here, let's call it last. And so this one means we pick a 0. So put 0 there. And this one means we pick a 1. And of course, we have to return count. And that's it. That's actually the code that will give you the valid combination of bit strings with no consecutive ones. So we can try to run this code. I'm going to call it here. So equal to generate n, and well, with the first pick, it doesn't matter if you pick a 0 or 1, right? So basically, it's like we have a 0 at the start. I mean, it's not really there. It's just that there's no limitation. So why are you not being happy? Because I forgot to put static here. Okay. And of course, I need to do the all important if last is equal to, sorry, not equal to 1, then you can do this. Otherwise, don't do it. So again, this is me picking a 0, line 21. And line 23 is me picking up a 1, which I can't do if the last bit was also a 1. So uncomment this and try to run it. 2 cases. So let's put in 2, we should get 3, and I put in 10, it's 144, which is what the question is asking. So let's check the question. Yes, 144. Oh, I also have to do this because the number can be so big The question wants us to reduce the value modulo 10 to the 9 past 7, which is just 1,000,000,007. So I'll put that here. Modulo 1,000,000,000. Okay. So this code works. It will give you the answer correctly, but this is just brute force, which means it's going to be very, very slow. The problem here is that the input n can go up to 100. Actually, forget that, it can go to 10,000. So let me show you what happens if I try to run this with something like 30. Let's try 30. All right, so 10 cases, let's try 30. Oh, that's still pretty okay. 35. Okay, that's actually still pretty fast. 40. Okay. So there's a slight delay there because it's taking a long time. Try 42. Getting slower. And this is not going to work with n equal to 10,000. It's not even going to work with n equal to 100. It's going to take days, and n equal to 10,000 is probably going to take years or millions of years. You want to know how big 2 to the power of 10,000 is? Because that's the number of combinations you have to work out. That's how big 2 to 10,000 is. So it's humongous. Forget about doing this using brute force. So what do we do? Well, obviously, we're going to solve this using dynamic programming. So in order to explain my approach, I need to go back to the drawing board. Let's do that. Remember, the main principle of dynamic programming is that you don't want to compute the same thing twice. Or maybe I should start saying you don't want to compute the same thing more than once, because you don't want to do it 3 times or 4 times either. So every time we arrive at a subproblem, we have to check whether or not we have already done the subproblem before, so that we don't have to do it again. Now, this is very obvious in the previous dynamic programming problem, the one with the pebbles, because you can clearly see that these two subproblems have the exact same input, so they're the same subproblem. But when I look at this tree, I don't see any overlaps. All these values are distinct. So how can we use dynamic programming here? Well, number one, the values in these nodes are not the input to the function, because as you can see in the code that we wrote just then, we're not passing the string. Our input was n, which is how many more bits we can append, and also the last digit of string, because that determines whether or not we can add a 1 to the string. So I can annotate this tree with that information. Well, I guess I didn't annotate all the way to the bottom when n is equal to 0, but I think that's obvious. And hopefully you can see the overlapping subproblems now, as in we're calling the function generate twice with the same input, here and here. Because in both cases, we want to add 1 more bit to the string, and the last bit was a 0. Now, these two are different to this one, because, well, we also want to add 1 more bit here. The last bit was a 1. That's why the structure is different. It's a different subproblem. Anyway, this is going to return 5, because all these valid nodes will return 1, and there are 5 of them. And in this tree, we start with an empty string up top, but what if we start with 100 and we want to make a string of length 6? Well, the decision that we're making are going to be the same to the one that we made earlier with the empty string, because either I add a 0 or a 1 at the start, and from then on, the structure will be exactly the same. We will return 5 as well, exactly the same number of combinations we have when we start with an empty string. What do you think will happen to this tree if I replace 100 with 010? We will still have 5 valid combinations. So the starting string doesn't matter. You can have nothing. You can have 100. You can have 010, because they are all the same problem. We want to append 3 bits to the string, and the last bit is a 0. Hopefully you can see the overlap now. You see, with brute force, we're doing the same thing again and again. Let's say we want to make a string of length 6. With the brute force method, if we start with 100, we have to do all these subproblems. Then, if we start with 010, we have to do all these subproblems again. And we have to do it again. We start with 0, 0, 0, where in fact, we know that the answer will always be 5. Do you see why this is a waste? But what if we start with 1, 0, 1, or anything ending with a 1? Well, we can't have this combination anymore now because you're going to have consecutive ones. So there are only 3 possibilities. Which means that if we want to append a string of length 3, then there are 5 possibilities if we're adding to a string ending with a 0, and only 3 if we're adding to a string ending with a 1, for a total of 8 combinations. So how many valid strings of length 4 are there? Well, these 8, because you can either start with a 0 or a 1. So is there some sort of pattern here? Okay, some of you probably already figured this out, but I'll go through it anyway. If you think you already know how to code this, then go for it, or skip to the part where I'll start writing the code. If you're still unsure about the pattern, think about this. How many combinations are there if we want to append a bit string of length 4? If I have a string ending with a 0 and I can append 4 more bits, how many unique strings can I make? What if it ends with a 1? Well, these are all the possible bit strings of size 4. There are 8 of them. So if we want to append these bit strings, how many combinations do we have? So let's keep it simple. How many strings of size 5 can I make? Well, the 8 that you see here, I can append a 0 in front of it. Is that it? No, because these 5, instead of appending a 0, I can append a 1. Obviously, I can append a 1 to these guys. So there's a total of 13 combinations of length 5. So I wonder if you can see the pattern now. Let me summarize what we have observed so far. This should really clear it up. How many bit strings of length 3 are there? 5. Actually, why don't we go back a bit? How many bit strings of length 2 are there? 3. This is easy to see. So when we try to work out the number of bit strings of length 4, what do? We take the 5 of length 3, and then we add a 0 in front of them. Can we also add a 1? Yes, but not to all of them. We can add 1 to only these 3. But these 3 are derived from bit strings of length 2 by adding 0 in front of them. So it's like we're basically adding 1 0 to these 3. Can you see it? So from length 2, if you add 1 in front, then you'll get these 2. But if we add a 0 in front, we can later add a 1 and get these. Or to put it another way, from length 2, we're appending 0, 0, 0, 1, or 1, 0. That gives you 8 combinations. I hope you can see that. What about bit strings of length 5? Same thing again. You take these 8, and then you add 0 in front of them, and then you take these 5, and then you add 1 0 in front of them to have a total of 13. And this pattern will continue. If you're looking at strings of length 6, there's going to be a total of 21. By the way, do you know what this sequence of numbers is called? 3, 5, 8, 13, 21? Well, in case you don't know, this is the Fibonacci sequence, where the next number is the sum of the previous 2. I mentioned this in the previous video, in that every single introduction to dynamic programming that I have seen always start with computing the Fibonacci sequence. So here's mine, although I think this is less boring than just working out the Fibonacci numbers. So hopefully you can see the pattern, you understand the overlapping subproblems. Now let's talk about how to code it. Starting from the top, we have to make a string of length n. And we have 2 options at the start. We pick a 0 or a 1. And you've seen how this is done because we wrote this in the brute force code earlier. What you need to see now is that these 2 subproblems are the same because both wants to make a string of length n minus 2 when the last bit is a 0. So you have 2 choices here. You can pick 0 or 1. If we pick a 1, like here, we only have 1 choice. Here as well, for that matter. Furthermore, we know that if we pick 1, we have to pick a 0 after. Makes sense, right? You can't pick a 1 and then pick a 1 again. So we can actually skip this node. Because think about it. From top here, if we pick a 0, then we can append another n-1 bits. So we work out how many bit strings there are of like n-1. That's what we're doing here. But if you pick a 1, you really can only append another n-2 bits because you are forced to append a 0 after. So now you have to work out the number of bit strings of length n-2 that you can append to it. That's why you jump. And in fact, we don't have to worry about this part. Hopefully this makes sense. One more time. You don't have to worry about ending with a 1 because you must add a 0 after ending with a 1. So it's pretty much the same as a string ending with a 0. You only have to worry about strings ending with a 0. I hope that makes sense. So that's the plan. To work out the number of valid strings of length n, I need to work out the number of valid strings of length n-1 and n-2. To work out the number of valid strings of length n-1, I need to work out the number of valid strings of length n-2, and as before, we're going to skip this node because this is a subproblem of strings, well, of adding a string of length n-2 to a string ending with a 1. Yeah, that's a bit annoying to say, but hopefully you remember what this is about. This is when you pick a 1. So we're going to skip that. We're going directly to this n-3, where again, this problem is the same with these two. These are the problem of adding a string of length n-3 if we're appending to a string ending with a 0. This is all a bit of a mess to say precisely, but hopefully in your mind, you know what this is about. We're also going to be skipping this n-3. We're going straight to n-4, again ending with a 0. So we only care about appending to a string ending with a 0. And how will we actually compute this? Well, starting from the top, we're going to the left side. So we're going to work out n, and then n-1, n-2, n-3, and so we're going to go all the way to the bottom until we hit n equal to 0 here. And at that point, we would have computed the values for the function for all of them, from 0 up to n. So you store these values in a table somewhere, in an array, and then as you go back up, you will have to go to the right. But every time you go to the right, you already computed the value that you need. So let's say you're at n-1. So we go to the left, you go to n-2, you go to n-3, you go to n-1, so on. And when you go back up, you need to work out n-3. Well, you don't have to recurse further you don't have to recurse any further because you already have the value for this because you computed it here. Same way when you're at n, you don't have to go, well, you have to go to the right, but just for one level. You see that you need the value for n-2 and you have computed that here. So you don't need to do these two nodes. Hopefully you can see the savings here. So instead of like a big humongous tree, I mean, if you try to draw this tree, it's going to be a pretty big tree. You only have like one straight line to the left and then just like one level to the right on each node. You're only doing like 2n function calls or something like that. Okay, and this is exactly how you do Fibonacci. If you want to compute the nth Fibonacci number in the sequence, this is how you do it. Well, this is one way of doing it. This is what we call the top-down dynamic programming because we started from the top, we go into the bottom, and we store the result as we go to the bottom. You can also do bottom up. We're gonna do that in the next video, and that is when you actually build the table from the bottom. You can do that with the Fibonacci. You basically start from 1, and then you go 1 again, 2, 3, 5, 8, and so on until whatever n you need. Whereas here we start from the top and we recurse. There's a slight difference there. Hopefully you can see it. So that's pretty much the hard part, really. If you get this so far, you're good to write the code, and the code is actually very simple to write. And let's get back to it. Okay, first thing we're gonna do, we don't need last. because we now assume that the string will always end with a 0, correct? And what do we put here? Well, if n is equal to 1, then I'm going to return, what if one? There's only, sorry, there are two combinations actually, 0, 1. If n is equal to 2, the answer is 3. So I'm going to hard code those. And then, if it's neither of those two, I'm going to return generate n minus 1 plus generate n minus 2. And I still have to do modulo 1 million something. That's it. That's the code. Well, as in this will do this part here, but there's no dynamic programming at all. So change that into n. So let's run this again. 2 cases. 2. Was that 10? I think it was 10. Yep, 144. So this is correct, but this is still slow. If I put in, let's put in something like 40. This will still take a while to finish. So how do we do the dynamic programming part? Well, as I said here, we're going to go all the way to the left because we're going to keep on calling this function here. We're going to go n minus 1, n minus 2, and so on. And every time, let me stop this first. And every time we get a result, we need to store it inside the table. So I'm going to make an array, public static int, it's called dp. And how many do I need? Let's just make it 10,000 because that's the limit. So 10,001. So this is where we're going to store the results. And all you have to do is, when we call generate, we can ask, well, if dpn is not equal to 0, means that we have computed the value, and if we have the answer, it can't be 0, right? So when we initialize the array, everything's going to be 0. So every time we call generate with the input n, first we check, have we done the case for n? If we have, then this will not be 0, and we just return that. If we haven't, okay, we need to work out the actual answer. So we have to call generate n minus 1 and generate n minus 2 to modulo that. But we actually don't need all this. Well, sorry, we need this one actually. We need that up top. We don't need these two actually, because what I can do is I can say dp1 is equal to 2 and dp2 is equal to 3. Okay, so don't need that. Okay, so if we have computed the answer before, just return it. If we haven't, then we need to store it somewhere. So here, instead of returning that, we're going to say dp n is equal to that. And then we just return dpn. Okay, so again, if we have done it before, return the answer that we have that we computed before. If we haven't, then go compute it and then store it in the array. Just going to run this now. 10 cases. So 2 should give us 3 still. 4 will give us 1. Oh, sorry. Yeah, 4 will give you 8. It was 10, wasn't it? 10? Yes, 10 will give you 144. Now let's try 40. Since faster, let's try 50. Let's try 100. Let's try 1000. Let's try the number that we have to, the limit, which is 10,000. And you see how amazingly fast that is compared to what we were doing before. This will not take millions of years. Well, that took like less than a second. That's the power of dynamic programming, because you are reducing the number of calculations from what is like 2 power of n, which is something like this, into 2 times n, which is 20,000. Am I going to submit this? I'm pretty sure this is going to get accepted. Well, I'm not gonna bother submitting. You can try to submit this on your own. I'm sure it will get it submitted. I will submit after I finish the video. I will submit it, and if there's a problem, I'll get back to you. But if there isn't, I guess that's it. I think this is a very long video, and it's getting harder. So yeah, hopefully you get something out of it. But anyway, that's it for me. Thank you for watching as always.